Now we'll look at general description. At x1 up to xn, denote the sample on which our confidence interval has to be based. So to obtain the confidence interval, we need a random variable which satisfies these properties. In the last case, we took the standard normal variable z after standardizing the sample mean. It satisfies both the properties. The variable z depends on the sample here. It also depends on the parameter mu, but the distribution does not depend on theta. Whatever the value of mu, the distribution remains standard normal. Oops, has to be n. Okay. So let me now go back and edit. And a specific random variable with some distribution. So till now, that specific random variable was the standard normal random variable z. Of course, it had a standard normal distribution. Let's come back in. Now, there's very limited content that you have to do in this unit. So you'll be dealing with two original random variables. Two original parameters. One is the population mean mu, and second we'll do just now, the population proportion. Okay, both of them have to be standardized this way, and the properties will be satisfied after we standardize it this way with a come up with standard normal variable. कोई issue नहीं है, but we have to be technically correct when we write the general description. That's why we have to write these specifically. If in some of the advanced courses you might have to do I might have to estimate some other parameters, then you'll have to be very careful in coming up with another random variable, whether that new random variable satisfy these two properties or not. Next, the recipe is, after this, we need to find values A and B such that probability, okay, I have not, suppose a random variable, the description of the random variable x1 to xn theta. So is equal to 1 minus alpha. Okay. The counterpart that we have done is a less than z z alpha by 2 minus z alpha by 2 plus z alpha by 2 is equal to 1 minus alpha. This is what we've just done. Okay. Next, we need to isolate theta like this. One minus alpha. So we did this minus z alpha by 2 into root n mu x bar plus z alpha by 2 sigma root n is equal to 1 minus alpha. Okay, what is written is black is specific to the parameter population mu that we had done in the last class, but is written in this other color is the general description of the exercise that we have to do. Now, and the lower and upper confidence intervals, confidence limits. Okay, that is a general recipe. In the normal case, this was the lower confidence limit, this was the upper confidence limit. Okay. Next, move to section 7.2. This was 7.1. So I'm doing the first half of 7.2, which is large sample. The section is about large sample confidence intervals. Part A is large sample confidence interval for mu. Will not make any assumptions about the population being sampled. including the assumption about knowledge of standard deviation of the population. Okay, these two were the restrictions that we had placed on ourselves in the last section, that the population being sampled is normal and knowledge about standard deviation of the population was available. Now we're relaxing these two. But here, adding one restriction, that the sample being taken is large, and with the rule of thumb that n is greater than 30. Okay, so we'll invoke CLT, the central limit theorem, and use S as an estimator of sigma. Okay, of course, this also adds to the variability. And some variability would be there because of approximation. Okay, so from 7.1 to 7.2, we will have less precise confidence intervals, if I can put it that way. Which part, Anindita? The one on the screen right now? Okay, I'll do that. Give me a moment. Not just last section, from 5.4, we know these facts. If population being sampled is normal, X bar is normally distributed. Okay, and we're speaking of estimating the population mean mu using the estimator sample mean. Okay, so if we have precise information about how the sample mean is distributed, we'll have more precise confidence intervals. Okay. And we are standardizing X bar as Z equal to X bar minus mu ओके बाद में हम ये म्यू अलग सेग्रीगेट कर लेंगे. We had information on we are assuming that if we have information on standard deviation if we have precise information on population standard deviation, then we have precise information, or Z is precisely standard normally distributed. Okay. Now what we have is, we don't know how population is distributed. Okay. Then as n gets larger, x bar is approx normally distributed. Okay, this word approx is there because we are approximating the distribution. The confidence intervals again would be approx, and 2 sigma is not known. So Z being standardized according to this expression, this also adds. Okay, for a stand variable to be transformed into a standard normal variable, we have to subtract mean and divide it by its standard deviation. If the standard deviation is again being estimated, then this Z has another element of approximation. Okay, now we have two elements of approximation. That's why I've written here some variability because of normal approximation of x bar itself, and some variability because on account of x bar being transformed into standard normal. ठीक है, अब मैं लंबा लिख नहीं रहा हूँ. Got it? इसको नीचे ले जाते हैं. कौन सा है ये? Oops. Give me a moment. Let me join again from the other account. And then we have for z equal to x bar minus mu Now, because of approximation, we're not writing equal to, we're writing approximate. This probability is approximately equal to 1 minus alpha. You can manipulate this, and z alpha by 2 into s by root n. And minus alpha, and x bar plus minus z alpha by 2 s by root n is 100%, 100 to 1 minus alpha percentage confidence interval, percentage large sample, CI for mu. Okay, I'm leaving out a very small subsection, which is the general large sample confidence intervals. I've already done general confidence intervals and specific large sample confidence intervals. You can combine the two to do that. Moving to confidence interval for population proportion. Make a guess as to why this particular subsection has been placed in section 7.2, which is about large sample confidence intervals. Okay, think about this point as I do this section. Let P denote proportion of successes. In population. Okay, their success, the word success has already been discussed when we were doing random variables. Provided n is small relative to uppercase N, which is the population size. What would be the distribution of this random variable x? Binomial. With expected value equal to n into p and standard deviation n into p into 1 minus p. Okay, of course, this is the parameter value, Okay, now we move to the approximation stage. If both n into p greater than 10 and n into p into 1 minus p is greater than 10 and n is sufficiently large. Okay, we discussed these things in the section on binomial. Then X has approximately a normal distribution. Okay, because of this, n is sufficiently large is caveat. This particular subsection has been placed in 7.2 in large sample confidence intervals. It is not going to work out if n is 4 or 5. Okay, so after this, it's relatively simple. We have a random variable which is normally distributed. The exercise would be to estimate estimating population proportion P using sample proportion P hat. Okay, this also we have seen P hat defined as X by N is an unbiased estimator of the population proportion mean. Okay, now what we need is we need another random variable which satisfies the two properties mentioned at the beginning of the lecture. That random variable is the standard normal. Okay, now how do I claim that p hat follows normal distribution? With this X is normally distributed, p hat is also normally distributed, because it's just random variable x divided by a constant. If p hat is normally distributed, we can standardize it by subtracting p and dividing by subtracting the mean and dividing by standard deviation, which I've already written. There's also still an element of approximation because we are approximating binomial using normal. Okay, uh, this exercise gets difficult at this stage when we manipulate it, putting p in between. So it will be, because we have p here and we have p in the standard deviation as well. So it will be p hat plus z square alpha by 2 to n 1 plus z square alpha by 2 into n I don't have enough space to write this entirely. So I'm going to just write the confidence interval. Okay. 100 into 1 minus alpha percentage confidence interval for P. Okay, so from this to this, you'll have to work hard to manipulate it. Okay, there is again a tiny bit of approximation for under certain conditions for N. For that, you'll have to read the text. And last, you need to do one-sided confidence intervals. Okay, so till now, what we've been doing is something like this. And this exercise is only for mu that I'm doing. You take out area alpha by 2 here, area alpha by 2 here, and you have the lower confidence limit and upper confidence limit. Okay, under the assumption that because of the uncertainty, the value that you get can be either a little higher or a little lower than the true population mean. If this is two-sided CI, if you have some knowledge about the problem at hand and feel that there's no chance of the actual value being lower than the true population mean, if because of randomness it's only going to move to one side, then you have to select upper confidence limit such that this area is alpha not alpha by 2. In two-sided, we just take out alpha by 2 from both sides. In one-sided, and we don't really have an interval, we just have one confidence limit. One-sided upper confidence limit, and similarly you can have a one-sided lower confidence limit. This area must be alpha. Okay. For mu x bar plus let's minus here z alpha into n by root n is lower one-sided ci x plus z alpha into s by n is upper one-sided ci. There's nothing special about this. All right, that'll be all for today. I'll see you tomorrow.